So we're discussing today this new physics and open problems. To some extent, I think it's maybe, at least for me, the more fun lecture, in the sense that I'm going to be posing problems. I don't know how fun it's going to be for the audience, because to some extent I don't have the answers to those questions. But there lies room for progress in principle. So I think this actually lecture is, in some sense, a window on areas of potential future research in the area of understanding the atmospheric circulation of exoplanets. I feel I need to justify a little bit more having a whole lecture on this, like, new physics and open problems. And the way I can sort of do that is by reminding us that simulating is not understanding. And so the way I organize the lecture, the first lecture I sort of went over the basic physics needed, the equations, the regimes of atmospheric flows that we expect on extrasolar planets. And then the second lecture was sort of a presentation of key results that have come out of actual simulations of the, if you will, the climate on exoplanets. And it tends to be 3D, time-dependent, sort of heavy machinery, and they give actually results that are interesting. But as illustrated by the title of this paper, it's not because you're able to simulate even successfully a system that you actually have gained any understanding. And so this guy, this scientist, Isaac Held, is a prominent atmospheric dynamicist. And he wrote this paper on this topic. I mean, half of the paper is about how, it was in 2004, you see, about how climate model got to be very detailed and very good at actually modeling the climate. But he was a bit appalled, I guess, or concerned with the fact that actually the level of understanding of what was going on in simulation was not following. And to a good extent, this is a little bit what's going on with extrasolar planets. I think I showed you this result of these simulations, but there are things that work, there are things that we think we understand, but there's a lot of things that actually we don't understand. So pushing this argument to the extreme, I suppose, a little bit maybe a circular argument, or I don't know how much you'll buy it, but to the extent that I were able to simulate the entire universe on a computer, which is, of course, is not possible, what I would get for them one simulation is just a second realization of our universe, and I would have understood nothing. So a simulation itself has no value. With a build-up to that simulation, what the physics you need to put in all the failures of that simulation, getting to that successful simulation is where you actually understand things. So this is why it's worth, I think, spending a whole lecture about, the problems, because the problems are signs of evidence that we can understand more, and there are pathways to understand more about what's going on in these atmospheres. So I want to revisit a little bit this, I want to revisit one of the issues that was mentioned briefly yesterday, the issue of the lower boundary on giant planets, the modeling of extrasolar giant planets. Then I'll tell you a little bit more about magnetized atmospheres, the fact that a lot of exoplanets, the problem, contrary to what I told you, and I led you to believe, probably hydrodynamics is not a good approximation, and we actually want to treat this atmosphere in MHD, non-ideal MHD. I want to just emphasize some of the issue we have with these winds being supersonic on hot exoplanets. And then I do want to say a few words about the business of radiation hydrodynamics, in the sense that it's not entirely obvious to me that the radiative transfer that's done for exoplanets is actually accurate enough that we can trust it entirely. And it's, I'll get to argument and explain what I mean by that. So issues at depth. You remember that plot of the super-rotating circulation regime where you pump up angular momentum towards the equator and you get this super-rotating equatorial jet. And I did emphasize a little bit the fact that it appeared that this model started at rest. So everywhere you should get zero velocity. if the flow didn't feel any change from the initial condition, you should get the zero velocity. And at depth, you get negative velocity. So while you pump up angular momentum here, you have now a deficit of angular momentum here at depth. So it appears that even though these layers are inert, they are not forced by the radiation from the sun, they actually are coupled to the weather layered. And so that raises a little bit the issue of how deep that coupling goes. Because at the bottom here, we cut in this specific model, but I think it's representative of what people do for hot Jupiters or warm mini Neptunes. We cut here at 200 bars, and I mentioned that we have a material surface here, meaning there is no exchange here. In some of the models, people put a heat flux, the interior heat flux in the radiative transfer, but that's all there is. And so if you're able to couple down, the question is how far do you couple? Does your flow here fill the lower boundary condition that actually you have set, which we know is not a physically sound boundary condition, because we really limit the flow from going through that layer, but actually it is. The actual flow would go through that layer, is allowed to go through that layer. So this is something that has bothered me for years now, and I have not quite been able to tackle that problem satisfactorily, but actually I had a discussion with Pascal yesterday that was actually very illuminating, and I think there might be a way of doing things better here. So let me mention something. So of course, I'm not the only one who was worried about this, and I think the other people have actually done the same exercise of saying, let's cut, instead of cutting at 100 bar, let's cut at 200 bar or 300 bar and see whether the depth of the atmospheric layer we model has any effect on the layers that we are interested in terms of observation. The weather layer is where you emit also, you force from insolation, you irradiate in infrared, and that's what we care about from an observational point of view at least. And there is evidence that the model results do not strongly depend on where you cut there. So that seems reassuring. But that's actually a misleading, I think that's a misleading fact. Because if now you look at one of the simulations that's run for very long, and you just on each of the layers. So now as a function of pressure, you go on isobars in the model, and you calculate the total kinetic energy of the wind. And you ask, so quickly, where you force actually the wind, you get to establish a steady equilibrium to some wind velocities that stay steady from the forcing, plus whatever friction there is actually in the model. Remember that I'm also worried about what's the nature of the friction, but I won't get into that right away. But the point you see that basically the coupling from the weather layer, high up here above 1 bar, to the deep layer happens slowly and slowly and slowly and slowly. And then we're limited by computational power here. It's really difficult to push things to tens of thousands of days or beyond. So another way of thinking things is that this plot shows you that the models are not equilibrated in the sense that the flow has not necessarily been able to interact properly with the lower boundary condition. Another way of thinking that this is that the flow you're seeing in all of the simulations are transients. We have applied mathematicians in the room, and they'll tell you that when you solve PDEs, it's sometimes as important to deal with the boundary condition as with the equation themselves. The boundary conditions can be very important in affecting the flow. So I'm quite worried about this, the fact that actually those flows that we're using are not equilibrated with the bottom. So now there is something that Pascal, so I'll get to the discussion I had with Pascal yesterday, which I think is rather interesting. She was mentioning, and I'm paraphrasing here, so she's going to correct me if I say something wrong. She had some interest in a related problem, maybe somewhat idealized, but it would actually lead to some understanding, I think, in this case, which is the fact that, she mentioned to me simulations where they would mechanically force at the top boundary in a rotating fluid, mechanically force the flow. So, this is thermally forced, but the difference, I think, is not that important in that case. And try to understand how deep the forced layer will actually couple to unforced layer at the bottom, and to what extent, depending on the stratification, the degree of stratification, so by that I mean stably stratified, how stably stratified the flow is, how deep the circulation penetrates, and therefore to what extent it's able to fill the lower boundary condition, or actually, if you have a very strongly stably stratified flow, you force at the bottom, you do actually develop a flow at depth, but it decays exponentially. I think this is what Pascal was saying. And effectively, it actually does not necessarily feel strongly the boundary condition that you have at the bottom. So I think that might be a way, actually, of trying to answer this business here. You know, how deep do you have to go to put a boundary condition that we know is not quite physical in this problem? And are we doing things right? Or could we actually, another way of saying this is, if we were able to integrate for a very long time and actually have this flow feel the properly equilibrate with the boundary condition at the bottom, would things change? So that's one of the worries I have. And there is no answer because it's just completely not possible to do. Same problem exists to some extent for giant planets in the solar system, but things are a little bit easier there because you just have to go to one bar, not like hundreds of bars to reach the convection zone. Now the convection zone itself is interesting. You don't want, in general, to model the convection zone with a primitive equation of meteorology because convection zone is an unstable stratification, and so the only way you can treat that with primitive of equation of meteorology is to keep adjusting your TP profile to a neutral stability. So it's not a very good way of doing things, really. But this raises to me another issue, which is the fact that on top of this issue of the boundary condition we have here, the fact that just below here, there is this active convective layer. And so one of the things that's going to happen is that those convective blobs going up and down, they're probably going to excite some waves, typically gravity waves, at the boundary. And those waves might be able to propagate. And actually, how high they would propagate has not been worked out. And to what extent they would affect the flow here, coupled with this atmospheric flow here, is also something that has not been looked at. So that's all I'm going to say about this topic. But I think what I'm trying to convey is that we have issues at depth in these models that have not been properly addressed. And they make me somewhat uncomfortable. Yeah? Yeah, so this gets into, I'd say, if you look at the literature on atmospheric dynamics, people have come up with a way of diagnosing, to get diagnostics of flows, whether they're zonal or meridional, and by and far, those diagnoses have not been applied to this simulation to try to really understand what's going on. So I think that's a shortcoming of, as a community, we have not really done that. And so those diagnoses would actually, you could look at stream functions, things like this, actually, that are used typically to look at meridional flows, for instance, to understand what's going on here. And I'm fairly confident that there is a pretty interesting meridional flow going on here to explain that coupling, but it remains to be seen. Yeah.
Some of these are also rated quite deep, so capacities are very, very uncertain.
What is uncertain, sorry?
Capacities. So some of the models, the radius are quite deep, but the capacities and the pressure body is very uncertain. So especially since these mechanics are very thin capacities, that's what I'm worried about.
I see. So maybe someone who does radiative transfer can comment on this. Jonda is not here, but if someone else wants to comment. I was not under the impression that there is significant issues with the opacities. More importantly, is the composition, maybe. You don't know if you're dealing with 1 times solar or 3 times solar. And maybe that's what you mean. It's just, there are uncertainties, yes. Yes, and it's difficult to okay. Okay, are we talking about percent effect or factor of 2 effects? Okay. Okay. Yeah. Any other comments or questions? All right. So that's one of the first gray area, I would say, in the modeling of this hot exoplanet. And of course, this carries over to modeling of any deep atmosphere to the extent that we have to cut off. It's very difficult to model more than 5 or 6 orders of magnitude in pressures. And you already have, well, probably I would say, to get to model properly the radiative transfer from the solar insolation to the IR emission, you actually do need to model like a good 3 or 4 orders of magnitude. Then you try to go deeper, and then you run into the fact that computationally it's just very difficult. Yeah.
So is this problem also?
Yes, that's a good question. So that's going to fit a little bit in what I'm going to talk about now. So there's basically at least 2 schools of thoughts, I think, on the GCM of giant planets. And one of those is Tapio-Schneider group. And what he has argued for is the fact that you actually need to account for the fact that at depth in Jupiter, for instance, but it also applies in Saturn, and the depth is not so deep. It's significant, but it's basically 90% of the radius, you get into the MHD regime, something I'm going to talk about now. And that would lead, to maybe some form of rigidity of the fluid, because when you have a magnetic field, you try to actually stretch the magnetic field, the field will resist. So one way they have modeled that for Jupiter is to say that there should be some form of weak bottom drag. And bottom drag is nice, because once you put drag, then you are not trying to equilibrate. You sort of know what you're dealing with at the bottom, and then your flow has to equilibrate with that drag. And so that's, I think, a good way of avoiding this problem of having a material boundary layer, which is not very physical. So that's actually one of the things that has been done, and I think that's a good way, a good approach. And I think that's one of the things that should be done for hot exoplanets, to actually have an idea of how to put some drag and what the timescale for the drag based on MHD. And I mentioned that. In fact, I have done that in my model of JG1214b. I have put drag for that reason. So, and I'll get to explain that a bit more now. Any more comments or questions? Yeah. Yeah, I think there's a lot of similarities here. So maybe you want to say what the tachocline is, because some people probably don't know in the room. Oh, but the tachocline is this region in between the convection and radiative zone on the sun, right? Where a lot of interesting things happen. And people believe that's maybe where you generate the magnetic field of the sun, etc. So I just meant that, yeah. Okay, magnetized atmospheres. So the point is pretty simple, actually, and it's the following. If you look at, well, first, look at the Earth. There is a magnetic field on the Earth, but the atmosphere, and by that I mean the troposphere, stratosphere, is neutral. It's cold. So it doesn't care about the presence of the magnetic field, because if the fluid is cold enough that there's essentially very few charges. This is no longer true in some of the thermosphere and things that are going on really high up in the atmosphere, but I'm not talking about this. The bulk of the atmosphere is, to a very good approximation, neutral, so it flows through the magnetic field as if it weren't there. And that's true for Jupiter as well. It's cold, and its wind pattern doesn't care about its magnetic field. Of course, as you go deeper in Jupiter, you get into regimes where actually the fluid becomes partially electrical. It becomes an electrical fluid, and then rotation plus electrical fluid, conducting fluid, lead to the potential of the generation of magnetic field, and that's how you get the magnetic field on Jupiter. So the question is, where is the transition region? And I did mention that just now in answering one of the questions. Actually, you can do the analysis. There's this one way of looking at this is looking again at the dimensionless number called magnetic Reynolds number, and you ask when does it make a transition above or below unity. You can do that like order of magnitude, and that's about 90% of Jupiter radius. So it's fine. Above 90% of Jupiter radius, you can treat all the flows in the convection zone and the atmosphere as neutral, but below that, it becomes a magnetized fluid. Now, when you have a magnetized fluid, and when you need to care about MHDs, there's sort of two distinctive regime. One is where the fluid is poorly coupled to the magnetic field. So it's mostly neutral with a few charges, and that's called the regime of non-ideal MHD. So it's like MHD, but you need to account for specifically for, let's say, the resistivity of the fluid. Well, in general, you always need to care with resistivity of the fluid, but what you have is that the fluid is able to slip through the field line rather well. Even though it fills the field line, there is a fair amount of slipping through. And then in the regime where actually you get essentially a plasma, a fully ionized fluid, like stars, for instance, at the surface of the sun, then you are in a regime that's essentially called ideal MHD. And so as you go to cool planets to hot stars, and hot Jupiters are in the middle, you get this level, the pressure level at which you get to be MHD go up and up and up and up and up. And so hot Jupiters are interesting in that point of view, is that they are sort of a new class of transitional objects. They are in the regime of being marginally magnetized atmosphere. There are atmospheres that to a large extent are neutral, but there is a component, let's say a part in a billion, it's small, but that's enough to matter. A part in a billion of all the particles are actually electrons and ions, protons. And then because you get to collide the neutrals with the electron and the protons the electrons and the protons themselves feel the magnetic field, and they get stuck on the magnetic field, there is effectively a coupling of the neutrals, the wind, with the magnetic field. And so that's a regime of non-ideal MHD. And so this, the relevance of this regime was realized just a few years ago. The group at Caltech and then my own collaborators, we worked on this problem. And then since then, it's been evolving and developing. It's a tough problem. MHD is always tougher than hydrodynamics. And but I can sort of describe for you the basic ingredients that are involved in that scenario. And so what you have is weakly ionized wind. And again, you get mostly neutral hydrogen, neutral helium. But because you have solar composition gas, there is a small amount of alkali metal, like sodium and potassium. And those have very shallow potential well for the first electron, so they get very easily ionized. In fact, they get ionized, typically, I had the number here. The sort of temperature you want to care about is 1,000 to 2,000 Kelvin, depending on pressure conditions. So when you start reaching those temperatures in an ideal gas, you start having a population of free electrons and ions. And then, because those collide with your neutral frequently, you basically start being in the regime where there is a coupling to any magnetic field. And so if you think now about what I described to you, this super rotating equatorial jet, the wind that we have seen, I've shown you several of those on the wind profile. What's going on is that, so this is now a cut of a planet here, and the arrows here are the electrical currents. So ignore that for a moment. What I showed you basically is that we have established, it seems, that hot Jupiters and a lot of exoplanets have actually this wind going this way. Now, if you believe that you have a line dipole, the simplest magnetic field generated from the bulk motion inside. So the same way you generate the magnetic field of Jupiter, say, or Saturn, you do that on a hot Jupiter, and so you have a dipolar field. These are the field line, like this poloidal field line. And then the wind goes around like this, and if it were perfectly neutral, it would just go like this and not feel that there is actually a magnetic field. But because there is a residual population of charges, it means those charges couple to the field, and they prevent those charged particles from going around the equator, say. And then by collision with a neutral, which actually are being accelerated through this pump-up mechanism that I've discussed actually, are dragging the charges. So the net effect of that, if you just, one way of looking at what's happening in a non-ideal MHD framework is that you're generating a toroidal field. What's called toroidal in MHD means zonal in meteorology, right? So it means along a latitude circle like this, okay? So you start with a purely poloidal field, meaning axisymmetric, and then toroidal is creating a field going along the equator like this, if you will. And that's what the magnetized fluid does. The fluid is coupled to the field and it drags the field with it. That's one interpretation of what happens, I suppose. And so you generate a field here by coupling, and then the field resists that. A magnetic field doesn't like being twisted. This is called magnetic tension. It resists. But then you apply a drag on the wind. So then there's one effect, one physical effect that I call magnetic drag. Sometimes it's called Lorentz drag. It's the same. So basically, there is a brake on the wind. But on top of that, because you generate a field, you have to satisfy Maxwell's equation in MHD. You actually must, to sustain that toroidal field that you have created by entraining the field with the wind, you must create this poloidal current loop here that I represented. So you create actually electrical currents that go deep into the planet. And the planet being not perfectly a perfect plasma, those electric currents collide with neutrals. They get a finite resistivity in the medium, and so you dissipate this current through Joule mechanism. And so you heat up the planet on top of that. So there's two effects basically from this appearance of MHD phenomena in this non-annual MHD situation. One is that you drag the wind. This is magnetic drag. And the other is that actually the kinetic energy that you remove from the wind, by dragging, you reduce the velocity, you remove kinetic energy. That kinetic energy can be deposited at depth in the planet. And that's really nice because actually we know now of many hot Jupiter that are inflated. They appear to have a constant rate of energy being deposited in their interior. That's the only way we know of explaining their puffed up radii. And that's perhaps the leading scenario to explain that phenomenon. Even though the actual derivation, and there is a debate, I think, in the community about whether it works or not, it's an interesting mechanism because this physics is not new. It's been looked at, it's known, and it is there in those planets. The question is, how strong is it? Can it explain the amount of radius inflation we see in extrasolar planets? And to what extent is the drag important in limiting the wind speed? You remember that one of my first lecture, one of the things I emphasize is that if you want to understand the wind speeds in an atmosphere, you need to know about the forcing and the friction. So what's really nice about this is that now we have a physical mechanism that might be a dominant source of drag. So we might have found what the leading friction is in these planets. It does not apply to Jupiter. It does not apply to Saturn. They are neutral atmospheres. But on hot planets, the magnetic drag might be the dominant source of drag. And so that's also why it's worth investigating. Beyond just the fact that it inflates the planet, it is an important process to drag the winds in these atmospheres. So this is just illustrating this hot Jupiter radius inflation. Basically, the idea is that you take a pure ball of hydrogen and helium, and you heat it up to the temperature of hot Jupiters, and the max radius you can sort of reach as a function of mass is about below 1.2 Jupiter radii. And we know of many planets that are above 1.2. If you put a core, by the way, things are even worse, because the core, or a lot of metals, will tend to shrink the size of the planet. So for these planets to be at that radius and have stayed at that radius for billions of years, it means there is a constant source of energy, a non-negligible source of energy that's heating them up. And one possibility, among other, there's a lot of discussion about alternate mechanisms in the literature, but one of the possibilities would be this ohmic dissipation. So basically, the winds are driven by insolation. They get to feel the break from the magnetic fields, and that energy, kinetic energy, gets deposited at depth. That's the idea in that scenario. And so now, somewhat of maybe sad news is that people working out through this scenario, they've sort of established that the region that's the most important to actually understand how much of the heating you get deposited at depth in a hot Jupiter, it's well below the photosphere. It's this region at depth that I told you doesn't equilibrate in these models, where we have not necessarily reached the asymptotic wind speeds. Actually, this is where you get to generate the most of the heating. This is where you get actually the most important region for the source term in the induction equation, is what I'm trying to say. So it's technical, but that region is really important for actually deciding how much you deposit at depth. And that's the region that we don't model well. And that's the region that is hidden from us because it's way below the photosphere, so it's hard to constrain. So that's sort of a bad piece of news, if you will. And so there are things that matter a lot. For instance, if you say that you change the intrinsic heat flux coming from the planets, there is some freedom in doing that on those hot Jupiters, depending on their history and formation history. You actually get to change the temperature profile. So you see this is PT profile with different flux coming from the bottom, from the interior. And these are changes that might not be too dramatic, a few hundred Kelvin, but they lead to order of magnitude differences in resistivity. And that has a big effect on this ohmic dissipation business. And so, yeah. Yeah, so that's right. So that's thank you for mentioning that. So I'll say something about this. We've established that the dominant non-ideal MHD effect up to about that level, 100 millibars, is actually resistivity and probably thermal. But it's true that above that, you get to photoionize. So actually, you do have to do a proper radiative transfer and follow photoionization to know the population of free electrons you get. On top of that, my own estimation suggests that you might get into, because it's low density, you might get into what's called ambipolar diffusion regime at low density. So you switch to another regime of non-ideal MHD. So there's a number of complications with this scenario. It gets to be complicated, yeah. But it's true that photoionization might be quite important higher up there. This region, by the way, are the ones that are probed by transition spectroscopy, right? So they are actually of direct relevance to observation. So here's sort of my summary slide on this whole magnetized atmosphere business. I could give a whole lecture or even two on just that topic because it's pretty heavy. So magnetic induction in those atmospheres will happen. The question is, what is the magnitude of the effect? In terms of the drag, how much you can drag the winds and how much you can heat up the planet. And they go hand in hand with each other, right? It's just, you get two effects from the same process. It's a difficult process to model well. To a large extent, not exclusive, but to a large extent it's been modeled as a 1D problem. But what I told you about the atmosphere being MHD is actually not even true globally. The day side is MHD, the night side is hydro. You get 30 orders of magnitude in change in the resistivity from the day side to the night side. It's a usually anisotropic atmosphere from the point of view of MHD. And that's because when you solve psi equation, which is the one that tells you the degree of ionization of an atmosphere in a thermal context, negating photoionization, it basically varies exponentially with the temperature. And so having such large temperature difference between the day side and the night side results to many orders of magnitude changes in the resistivity, which is this degree of coupling of the field with the flow. So it's a really difficult problem to do well in 1D. You have to do it multi-D. And multi-D hydro with radiative transfer and everything is almost, I can say it's basically not done. It's really difficult to do. But there is clearly room for improvement. So the model has been challenged. It's certainly true that there is very inflated planets. You know, some of the plot I showed you, 1.6 Jupiter radius. It seems really hard to do that with that process. So there might be something else going on. It's certainly a possibility. And then there are some people have claimed that the model falls short energetically in the sense that it will heat up the planet, but not enough to explain the radii. So it's still debated as a process. My own opinion here is that process has not been modeled well enough that we can already drop it out and saying it's not working. Some people are stating in the literature that it's not working, but I don't think they have done that convincingly. But the summary, I guess, from the point of view of this lecture is that we are dealing with magnetized atmospheres. And you might say, oh, it's a hot Jupiters, and really, it's a special case of the very hot planet. It's not. This is JG1214b. You see, it's a planet with an equilibrium temperature of about 500 K, 550, I think. And these are like TP profiles, okay? And you see you hit 1,000 Kelvin at 100 bars. So at the bottom of the atmosphere of JG1214b, you are in the MHD regime. Maybe there is MHD drag there. So even relatively cool planets with deep atmospheres will have that MHD region pop up almost up to the photosphere. So MHD for warm and hot planet is generally relevant. All right. I guess I'll stop here and take questions or comments if there's any about this. I didn't want to say more. Yeah. It's a very good, I looked at this. It's very interesting. So can you do an MHD formulation of primitive equations of metrology? And what I have seen is people looking at the thermosphere of the Earth. I think they actually do solve primitive equation and they add actually MHD term. I have never seen a formal, I mean, you know, MHD is not clean. We have applied mathematicians in the room, and I think they'll tell us that MHD equations, they are not, you get hydro very cleanly from Boltzmann equation, small number development, this is called Chapman-Enskog development, is clean and it behaves well. My understanding is that the MHD equation and the way they derive them, it's just piecing things together. There is no formal development. And they actually, and we can hear from the experts maybe, or people have opinions, and they don't behave as nicely as nicely as a hydro equation in an applied math sense. And so I have never seen an attempt to derive basically MHD primitive equations. But maybe someone has seen that, I don't know. Maybe it's been done. Yeah. So there's no issue of closures, you feel, on small scales? Because I think there are issues of closure on small scales. Yeah. Yeah. Yeah, I'm worried about non-ideal. Once you get into non-ideal MHD, ideal MHD, and you have issue. Mm-hmm. Mm-hmm. Okay. Okay. Yeah.
Just to check, not for what I understand.
So the resistivity, okay. The resistivity does increase. Actually, the resistivity, you see, can increase or decrease its depth according to this profile. But the key thing here that I didn't emphasize too much is that looking at this plot, well, I'm looking for this plot there, that if you dissipate energy in this region here, that is not really an efficient way of puffing up the planet. What you need is to deposit entropy in the convection zone. And so that's why people worry about what the deposition actually just below the relative convective boundary is what is the driver of the radius inflation. You can show that. And then actually what happens deep in the planet is not that important. So the key is just these layers here, and the layers at the top of the convection zone are the key for that scenario. And you want to deposit in the convection zone because the amount of entropy you have in the adiabat, basically you pick an adiabat, determines the radius of the planet. So that's why you want to go at depth. Does that answer your question? Which magnetic field? You're talking about the induced field? Yeah. Oh, no. So actually, to be clear, there is more dissipation higher up here in terms of energy per second. But that one gets radiated away. And actually, it tends to be small compared to the radiative fluxes again, because it's relatively solar. So there, you're right. Maybe that's your expectation, that there should be more dissipation here. And there is more dissipation here. The point is that if you want to change the radius of the planet, so for the radius inflation problem, you have to dissipate in the convection zone. So that's why we care so much about what happens at depth. Yeah. Yeah, that's right. Yeah. Any more questions or comments? All right. So let me go over two additional points. And the issue here is this supersonic winds and the fact that we might generally expect shocks in these atmospheres. So you'll remember that when I justified or when I discussed the primitive equation of meteorology, one of the assumptions that was in there is slow motion compared to the speed of sound. And that's certainly good or at least decent approximation and generally a valid approximation for solar system planets. But now what's coming out of this simulation from a hot and even warm extrasolar planet. So again, the JG1214b, which is not such a hot planet, actually also have essentially sonic crossing winds, transonic winds, is that you get supersonic winds. And so that means your assumption of slow motions relative to the sound speed is actually not satisfied. So you want to go back to the assumptions you made and ask, me making that assumption and getting something that violates my assumption in actually the realization of the flow, what can that mean? And the one obvious thing it can mean is that when you filtered out sound waves to satisfy hydrostatic balance here, those sound waves might be important. They might be important because in a transonic flow, in a flow with high velocity, like velocity close to the sound speed or exceeding the sound speed, let's say if you get two fluid elements to come at supersonic speed, so they'll shock, right? So right away you'll get a shock. But this is probably not what's going on here because the field organizes itself, in sort of nice way. More likely, I think, and at this point it's a bit of speculation, I don't have all the answers. More likely is that you'll get to generate sound waves of finite amplitude, and then they will stiffen and shock because you have actually this supersonic and transonic motion. And so this is a process that is totally ignored when you solve the primitive equations of meteorology. There is, my understanding is that there is only one compressible mode that remains after you filter out sound waves in the primitive equation of meteorology. It's called a Lamb mode, and it is a compressible mode, but only it's a relatively global mode. So it's nothing to do with local sound wave propagating. And so that would argue for not using primitive solvers to study the atmosphere, but go to full hydrodynamics. And some people have done that. And, but it's hard because now you have to solve sound wave crossing vertically your layers, and this is a very short time scale on which they cross, and you have to adopt a very small time step, or your code breaks down. This is a standard issue in hydrodynamics or in solving PDEs, that you need things not to cross too many cells over one time step for stability. And so there has been some progress recently about this. One person I should emphasize that has done this for a few years is Jan Dob Dixon. He has actually had he simulated hot Jupiter flows with a fully compressible code, and he did mention, I think, the possibility and the emergence of some shocks in there. Recently, I did mention that paper already. Former and collaborators have actually taken a full hydro code, simulated just the equatorial region of a hot Jupiter, so using a beta plane approximation. So it's just a local region. It's fairly extended, but a local region around the equator. And they show that in that model, they do get the equatorial wind speed, the equatorial super rotation wind speed that are comparable in speed to what the GCM have shown. But what they show that at low resolution, they get this nice, I apologize for the quality of the figure here. This is pressure as a function of time. At low resolution, you get these smooth figures here, but when they go to high resolution, they start to see a lot of time-dependent features here that when they diagnose their flow, they interpret as actually, indeed, sound waves that actually steepen and shock. So this is known as a weak shock, if you will. It's just basically a sound wave propagates, and then the peak of the sound wave travels somewhat faster because of compression. It's hotter. So the sound speed at the peak of the sound wave is actually somewhat higher than at the trough. And so it gets to steepen and steepen, and then when it becomes perfectly steep, that's when you have a shock, a weak shock. And then you dissipate the sound wave. And so this is suggesting that having these high velocities in these atmospheres requires you to have a compressible solver. Or at least, I guess, at this point, I would say, it's not been clarified to what extent having or not having those modes, the sound waves, in the flow is important for what's going on and the flow regime. But it seems like it could be an important process. For instance, it could act as a form of friction. If you generate a lot of sound waves from the atmospheric flow, and then they dissipate through these weak shocks, then actually that is a form of friction. So we're always looking for processes that we can model in terms of friction in the atmosphere, and that could be a form of friction that is not important on Jupiter and Saturn, but is important on hot Jupiters and warm Neptune. And so I won't say more. I think this is still not an unsolved problem, basically, but it looks like some of this is happening. And so we are limited by the fact that GCMs are great tools, but they don't actually permit these sound waves. By construction, they actually filtered out the sound waves, which might be important and play a role in the dynamics. If someone wants to comment or ask a question about this. Yeah. It might be, but you're like supersonic at the factor 10, say, max, or factor 5 or 7, and your atmosphere is still very thin. So actually, even sound crossing time vertically, yeah, this, remember my Earth picture, right? It's very, very thin. So what kills you is the vertical in general. Yeah, but you have a point. It's also a constraint. That's a constraint that we feel when we run GCMs, right? Because you still have to satisfy this also horizontally in GCMs. You have to go to small time set because of the fast wind velocities. Any more comments or questions? Okay, so I'm coming to sort of my last point here, which is a bit of an esoteric point maybe, but might be worth making, the issue of radiation hydrodynamics. So I wonder how many people in the room know about a book that's called Radiation Hydrodynamics by Mihalas and Mihalas? This is really astrophysics, right? Okay, so some people have heard about it. So here's the situation. I told you the way I presented things for solving an atmosphere is to say, let's look at hydro equation and then do a development in small number, get to the primitive equation, and these are the leading order equations satisfied in our scales. That's not quite true. The system we're starting with here is a fluid, a material fluid, plus a fluid of photons. So actually, the most general equation that I can think of, at least that you can write for this, is the Boltzmann equation for the material particle plus the photon fluid. And then I separated that. I said just like ignore the radiation for now. We'll treat it separately. And so that is, in many situations, it's okay, but not always. And the business of radiation hydrodynamics is exactly that, figuring out when is it that you can separate the treatment of the fluid from the photons, or when you have to treat them in a coupled manner. A typical example of this in astrophysics is the treatment of the CMB, the cosmic microwave background, the last scattering surface. You know, when the universe makes a transition from being opaque to transparent, the way people address this problem is they solve the coupled Boltzmann equation for the hydrogen gas, basically, and then the photon, and they do that together in a coupled manner. That's the way they have to do it, because you make a transition from actually being optically thick to optically thin, and that's the right way to do it. The nice thing for them is that a lot of things are linear there, so they can go to Boltzmann, but everything gets to be linearized. It would be a bit crazy to try to do that for an atmosphere in general. But so, the other thing that I should mention is that there is at least one area of astrophysics where people do care a lot about radiation hydrodynamics, and that's when you get winds from hot stars. So one of the things we are not able to, stellar astrophysics works great in many ways. It's a predictive theory, it works. But one of the things we are not able to answer very well is what's the maximum size, maximum mass of stars. And the reason we're not able to tell you what's the maximum mass of stars, you know, is it 100 solar masses, 200 solar masses on the main sequence, is because of radiation hydrodynamics and its complexities. You get to get winds that actually make a transonic solution. And so, the pressure from the radiation, the momentum from the radiation itself pushes actually this gas away. And the radiative transfer of that problem cannot be decoupled in any way from the hydrodynamics, because the winds reach sonic speed and beyond. So you can decouple hydrodynamics from radiation transfer only when you get subsonic motions. If you get supersonic motions, actually, you might be in trouble. So that's the point I want to raise here. We have supersonic motions. And as far as I'm aware, all of the literature in atmospheric science that I've seen, people are not concerned with this effect for good reasons. Winds are subsonic in the solar system, so it's fine to separate things. So let me, formally, if you look at the Mihalas and Mihalas, it's a standard textbook in astrophysics on radiation hydrodynamics. it will tell you that when you have fluid velocities that are much less than the speed of light, which certainly we're looking at what happens close to the horizon of a black hole here and GR and this sort of crazy thing, then what you do is again a formal development in small number. Yeah? So I'll get to explain that, I think. You tell me if I don't, yeah. The short answer is that lines are Doppler broadened, and that's set by the sound speed. And once you get velocity in the flow that are compared to the sound speed, then you can further broaden the lines. That's basically the short answer. And I get to develop that argument. So in the limit of velocities much less than the speed of light, which is certainly satisfied in all atmospheres by far, what you do is that you tell Boltzmann equation for the coupled fluid and the photon fluid, and you do a small number development, and then you can get an equation for the radiative transfer. So it's a radiative transfer equation to leading order in V over C. And it looks very much like what you might think is the proper radiative transfer equation. So this is, but the notation might be unusual, but basically this I is a specific intensity, so at a specific wavelength. R here is some location in the system, so where I sit, I have to solve it everywhere in my volume. N is along a specific optical path. That's just a notation. And then nu is a frequency. And then you get minus kappa tot, which is the absorption coefficient. So it's the K here is the absorption coefficient, times the intensity minus the source term. So if you go back to the basic of radiative transfer equation, you'll get something like this, actually, as an equation. And then you get this phi function here, phi of nu minus nu naught, which actually is basically describing, you know the total absorption coefficient for a line, but actually you need to, because you solve that spectrally, you need to know the shape of the line. And this is where the Doppler broadening of the line and the pressure broadening of the line enter. So this phi of nu minus nu naught here, the way it's treated in all of atmospheric science, as far as I know, is basically something like a Voigt profile. I mean, people who do radiative transfer, I hope what I'm saying makes sense now. If there are questions, please ask. And the key thing here is that to leading order in V over C, you actually get another term, which depends on the velocity of the fluid, and really depends on the velocity of the fluid along the optical path. And so there's a new term there, and then all of radiative transfer in atmospheric science, as far as I'm aware of, put this V to 0 here, and again, for good reason, speeds are subsonic. But when you get sonic or supersonic speed, then actually, if you get a gradient of the velocity along an optical path, you emit photons. So you have some photons from your Doppler broadened, say, line. You emit them. You have a source fluid element that emits those photons. Along the path, you get actually to change the velocity of the fluid, a good fraction of the speed of sound, of multiple times the speed of sound, even in an extreme case. And actually, that means you change the shape of the Doppler broadened line. So hopefully that's a key point. I don't know how good I'm at explaining that. The point is that you just don't get Doppler broadening from the thermal motion of your particles. You also get Doppler broadening effectively from the bulk velocity of the fluid, if you have differential of velocity that approach the speed of light. And so my sort of interest to in this is that actually this might be relevant. I don't know to what extent it's important. So again, I'm posing a problem. I don't have really the solution. But actually, this might be important for specifically, I think, hot Jupiters. You know, you do reach like, in fact, this zonal average here might be some, and this is a sort of a low velocity model. I did mention to you that we can reach a few times the speed of sound. And so what might happen, and what I want you to imagine is actually some infrared photons emitted close to the photosphere going in a slanted way, let's say from the equator, away from the equator. Somehow, it might actually feel the fluid element that emits it might have a differential of velocity relative to the fluid element that might absorb it. That is actually commensurate with the speed of sound. Some of those optical paths will achieve that. In that case, the radiative transfer is not statically, the way it's done in GCM and all of atmospheric is not the proper way of doing it. you will get to modify the shape of the line beyond your void profile. And the typical sign of the effect is that you increase the opacity. This is something that has been established in radiation hydrodynamics. You make the medium more opaque that way. So that's a question, whether when doing the radiation transfer here, we make errors at the level of maybe less than 1%, or maybe 10%, or maybe more. I don't have the answer. This will be important specifically for the infrared radiation. Thermal radiation is actually isotropic, essentially, a black body emitting. So you do get to get this slanted path. And the slanted path being important here to probe different regions of the flow with different velocities. And this might be particularly important to transmission spectroscopy. So in fact, Tim Brown wrote a very detailed 60 pages or more, I don't remember, but very long paper on transmission spectroscopy. He has one sentence on this. It's very easy to miss it. He says, and I will neglect the differential of velocities in the flows when I do this. And so there is this issue here that's an open issue, and it's not been solved. As far as I know, it could be that it biases basically our inference from transmission spectroscopy, that it biases our treatment of radiation transfer in hot atmosphere. It also could be, it's a bit marginal, it also could be that it's a small effect and we don't have to care about it. So I'll leave that at this point, and I don't have a better answer at this point. Yeah. Yeah, I think I just wrote a paper on this, pointing out this issue, and trying to make some estimates. I think there is a lot of room for doing a good model of this and trying to estimate even the order of magnitude of whether we get opacities wrong by a small amount or significant amount. I think it's an interesting topic. Or along the front of. Yeah, that's right. So for transmission spectroscopy, you might think I'm okay because if I go along the wind and have about the same wind velocity, it might be okay. That's right. So it really depends on differential from absorption to emission, And what you thought was optically thin might become optically thick that way. So it's really a tricky problem to do well. So again, I looked at this problem, just estimating the order of magnitude level is actually really hard. Yeah. Yeah. I don't think so. No, it's too cool, too cold. Yeah. Okay, so that's basically my last lecture, the pointing out issues, open problems, and not really having solutions for you, but I think there are nice areas for further progress. And I'll mention that I just went through this list of topics. I personally think, and I have actually one idea that I'm working on, that there is additional physics that has not been considered that will be relevant. And it's simply the fact that we're looking at warm and hot atmospheres, the regimes of the flow, whether it's MHD, diffusion, radiation transfer, all of this, they get into new regimes of physics, and they have not all been accounted for. So there is still new physics, I think, to be considered in this atmosphere. And I think that's a nice, interesting area for improvement. That's it. Yeah. Yeah, that's a good question. So, yeah, I don't know actually, but I think it's a good question because you make a transonic, you have a transonic flow. I don't know to what extent this might matter. Yeah, the question is, do you need this is important in hot star because what drives the flow is radiation pressure. So momentum of radiation. You're very hot, so radiation is bad at carrying momentum, but actually you get so much radiation in hot stars that actually is able to push matter a lot, right? I think in planets you get colder, so even though you do get transonic solution, you might still drive the flow by pressure gradients and not actually be in a regime where that pressure is a radiation pressure. Maybe that was related to what you're. Yep.
That effect you mentioned, maybe you before. I thought Peter Hofschild was quite sensitive.
We talked about collaborating about it, and he was supposed to run that because Hochschild has a full radiation hydrodynamics code, and I'm not aware of having him published anything, but maybe I missed something. Yeah?
I don't remember.
Okay,
He's the
so
only person I remember ever bringing this up before, but it wasn't in person. Something that maybe you wrote it down and thought of.
yeah, we exchanged some emails, and he was interested in actually looking at that problem, but it didn't go anywhere. Yeah.
I'm sure I wasn't on the email chain.
Yeah.
So this thing, you said that it all actually happened.
Yeah, so yeah, that's a good question. So basically the let me go here again. Sort of that's my representation of those atmospheres. They get a lot of dissipation here, but the ready fluxes are so dominant that actually I don't think it matters so much. Well, maybe on the night side, actually, it could have a, that's the thing, is that on a terminator where you receive less of insolation and you're sort of still marginally coupled, depending on the type of hot Jupiter, there could be an area where actually ohmic dissipation in the atmosphere is what set the temperature profile. But more importantly, I think it will matter here.
I guess what I'm thinking about is that's always, I think that's always
Yeah. Yeah. Yeah, so on the day side, like just looking at it quickly, it looks like radiation dominates. But I think on the terminator, I think it might be worth making a careful estimate. In some cases, you might actually get deviations from your TP profile because of ohmic dissipation. It's not impossible, I say. Night side is, that's the thing I was trying to say. You get MHD on the day side and you're non-MHD on the night side. It's really crazy. Yeah. 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 So actually, I've sort of proposed in a weak way, just by words, the fact that you might get a correlation between the amount of shift you get. If you drag the wind, you get maybe less shift in this hot spot, in the phase curve, and that might correlate to actually the amount of radius inflation. There's a lot of yeah, exactly. This is difficult. And the first thing you need to do is to solve that MHD problem well before you go and say, I can infer things from observation. So I don't know if in practice it will be doable, but I agree that in principle, they have to be correlated, exactly. The wind speed in some way and the radius inflation are now becoming tightly, if that's a leading mechanism that explains the radius inflation, they have to be correlated, yes. But some of the understanding comes from building a hierarchy of models, right? And then looking at extra processes and all this. The other thing that people talk a lot about in climate literature is a modeling hierarchy, going from simple models to more complex models. Because if you drop physics, basically the idea is that you reduce the dimensionality, then at some point you lose some of the effects, and from that you understand what matters. I think that's my way of looking at it at least. So. And so some of that has been done. For instance, the Schoman and Polvani paper on explaining superrotation, it just achieved that with a very simple minimal model, right? So some of that is being done. Some understanding you get of ohmic dissipation and magnetic drag from simple 1D model. So I think that's a way to go. It's a complex system. You need a range of models from simple to actually full physics as much as you can to try to disentangle the effect. Yeah. And the other thing I think that has not been done enough, because it's tough, is to diagnose those flows. It's all the same throughout astrophysics. You get simulations of galaxy formation, but actually to really know what's going on is actually a lot of work to actually finding a sound wave in a simulation like this is not easy. Finding shocks in a flow is not entirely easy. So having more diagnostics of the flows. Yeah. But so the way it goes, when you have crappy data, you can do with a crappy model. And crappy is a bad term, right? But when you have poorly constrained problem, let me rephrase that, then a relatively simple model is okay. When we get to JWST, we get actually real good data on these hot Jupiters, then we might find that, I mean, to some extent, Jonathan and Adam Sherman have pushed in a direction which is the way people have pushed in the solar system quite successfully. And I think their approach has been quite successful in fitting the phase curves and various observational data we have. At some point, the model will fail when we get good enough data. And at that point, you might want to really add the physics, right? Because that's one of the things that might be missing. So I think that's the way it's going to play out. In the meantime, there are low-hanging fruits. Just estimating order of magnitude effect, I think, is still there. And so it's good to just look at that from a pure theory point of view. And they give actually results that are interesting. But as illustrated by the title of this paper, it's not because you're able to simulate even successfully a system that you actually have gained any understanding. And so this guy, this scientist, Isaac Held, is a prominent atmospheric dynamicist. And he wrote this paper on this topic. I mean, half of the paper is about how, it was in 2004, you see, about how climate model got to be very detailed and very good at actually modeling the climate. But he was a bit appalled, I guess, or concerned with the fact that actually the level of understanding of what was going on in simulation was not following. And to a good extent, this is a little bit what's going on with extrasolar planets. I think I showed you this result of these simulations, but there are things that work, there are things that we think we understand, but there's a lot of things that actually we don't understand. So pushing this argument to the extreme, I suppose, a little bit maybe a circular argument, or I don't know how much you'll buy it, but to the extent that I were able to simulate the entire universe on a computer, which is, of course, is not possible, what I would get for that one simulation is just a second realization of our universe, and I would have understood nothing. So a simulation itself has no value. With a build-up to that simulation, what the physics you need to put in all the failures of that simulation, getting to that successful simulation is where you actually understand things. So this is why it's worth, I think, spending a whole lecture about the problems, because the problems are signs of evidence that we can understand more, and there are pathways to understand more about what's going on in these atmospheres. So I want to revisit a little bit this, I want to revisit one of the issues that was mentioned briefly yesterday, the issue of the lower boundary on giant planets, the modeling of extrasolar giant planets. Then I'll tell you a little bit more about magnetized atmospheres, the fact that a lot of exoplanets, the problem, contrary to what I told you, and I led you to believe, probably hydrodynamics is not a good approximation, and we actually want to treat this atmosphere in MHD, non-ideal MHD. I want to just emphasize some of the issue we have with these winds being supersonic on hot exoplanets. And then I do want to say a few words about the business of radiation hydrodynamics, in the sense that it's not entirely obvious to me that the radiative transfer that's done for exoplanets is actually accurate enough that we can trust it entirely. And it's, well, I'll get to argument and explain what I mean by that. So issues at depth. You remember that plot of the super-rotating circulation regime where you pump up angular momentum towards the equator and you get this super-rotating equatorial jet. And I did emphasize illuminating, and I think there might be a way of doing things better here. So let me mention something. So of course, I'm not the only one who was worried about this, and I think the other people have actually done the same exercise of saying, let's cut, instead of cutting at 100 bar, let's cut at 200 bar or 300 bar and see whether the depth of the atmospheric layer we model has any effect on the layers that we are interested in terms of observation. The weather layer is where you emit also, you force from isolation, you irradiate in infrared, and that's what we care about from an observational point of view at least. And there is evidence that the model results do not strongly depend on where you cut there. So that seems reassuring. But that's actually a misleading, I think that's a misleading fact. Because if now you look at one of the simulations that's run for very long, and you just on each of the layers. So now as a function of pressure, you go on isobars in the model, and you calculate the total kinetic energy of the wind. And you ask, so quickly, where you force actually the wind, you get to establish a steady equilibrium to some wind velocities that stay steady from the forcing, plus whatever friction there is actually in the model. Remember that I'm also worried about what's the nature of the friction, but I won't get into that right away. But the point you see that basically the coupling from the weather layer, high up here above 1 bar, to the deep layer happens slowly and slowly and slowly and slowly. So we're discussing today this new physics and open problems. To some extent, I think it's maybe, at least for me, the more fun lecture, in the sense that I'm going to be posing problems. I don't know how fun it's going to be for the audience, because to some extent I don't have the answers to those questions. But there lies room for progress in principle. So I think this actually lecture is, in some sense, a window on areas of potential future research in the area of understanding the atmospheric circulation of exoplanets. I feel I need to justify a little bit more having a whole lecture on this, like new physics and open problems. And the way I can sort of do that is by reminding us that simulating is not understanding. And so the way I organize the lecture, the first lecture I sort of went over the basic physics needed, the equations, the regimes of atmospheric flows that we expect on extrasolar planets. And then the second lecture was sort of a presentation of key results that have come out of actual simulations of the, if you will, the climate on exoplanets. And it tends to be 3D, time-dependent, sort of heavy machinery. A little bit the fact that it appeared that this model started at rest. So everywhere you should get zero velocity. If the flow didn't feel any change from the initial condition, you should get the zero velocity. And at depth, you get negative velocity. So while you pump up angular momentum here, you have now a deficit of angular momentum here at depth. So it appears that even though these layers are inert, they're not forced by the radiation from the sun, they actually are coupled to the weather layered. And so that raises a little bit the issue of how deep that coupling goes. Because at the bottom here, we cut in this specific model, but I think it's representative of what people do for hot Jupiters or warm mini Neptunes. We cut here at 200 bars, and I mentioned that we have a material surface here, meaning there is no exchange here. In some of the models, people put a heat flux, the interior heat flux in the radiative transfer, but that's all there is. And so if you're able to couple down, the question is how far do you couple? Does your flow here fills the lower boundary condition that actually you have set, which we know is not a physically sound boundary condition, because we really limit the flow from going through that layer, but actually it is. The actual flow would go through that layer, is allowed to go through that layer. So this is something that has bothered me for years now, and I have not quite been able to tackle that problem satisfactorily, but actually I had a discussion with Pascal yesterday that was actually very